Hello everybody, my name is Matthew and today we're going to prove that the normal distribution is a PDF. Now recall, what does it mean to be a PDF? So a PDF is a function that is positive everywhere and the area under the PDF is 1. Those are the only two conditions for a PDF to be a PDF. Now it's pretty easy to tell. If we look at the graph, let me turn on the pen here. If we look at the graph of a normal distribution, it's positive everywhere. We can see that. It's very easy to prove that, and so we're not gonna delve into that too deeply here. So basically, the domain of normal. This is how you denote it. Normal distribution with a mean of mu and a standard deviation, or variance of sigma squared. The domain of it is all real numbers, right? That's an infinity, that's infinity. The range of n sigma squared is going to be, it varies between every single normal distribution curve. So I would say it's at least zero. It's above 0, but then it goes up and then it'll hit some point and then it'll go back down. So yeah. So today we're going to prove that this normal distribution is a PDF. So we can't normally, when we look at PDFs, we think about, well, if we integrate it with the support set on the bottom, like if we integrated it from negative infinity to x over n u sigma squared dx, or actually no, it would be dt dt. Then, but the thing is, we can't integrate this function. It's not integratable by elementary functions. So we have to perform some tricks to this. And let me erase this. I'm gonna erase all this. Okay. So what is the normal distribution formula? The normal distribution formula is 1 over square root of 2 pi sigma e to the negative x minus mu squared over 2 sigma squared. That's the function of the normal distribution. So now, how do we tackle this problem? How do we show that the area under here is 1? How do we tackle this? Well, first of all, we still want to integrate it as far as possible. We want to integrate this function. So what we're going to do is we can realize that we want to, this part right here is a constant, right? This can come out of the integral, right? So let's prove instead the 1 over, that's 2 pi sigma integral from negative infinity to positive infinity e to the negative x minus mu squared over 2 sigma squared. So we're just taking this part, putting it down here, taking this and moving it out front. Now we want to prove that this equals 1. So sorry, that's my cat. So we should realize we want this part to equal square root 2 pi over sigma. We want this part because like this will cancel this and make it 1. Does that make sense? We want, because when we integrate this out, we want this to equal 2 pi square root of 2 pi sigma to be on the top. So that is what we're solving for, and that is what we were going to do. All right. Now, so there's a little trick here. So let's consider, let's call this part right here, let's call it C. So, so we want C to equal square root of 2 pi sigma. So let's consider, this is where the tricky part comes in, because if you don't know how to integrate this, becomes tricky. So let's consider c squared. We're not doing anything but squaring the c squared. So what are we doing here? Well, look at what c is. Well, we're going to integrate over negative infinity to infinity e to the negative x minus mu squared over 2 sigma squared dx. And then we're going to integrate again. That's what the squared means, over e to the negative x minus mu over 2 sigma squared. This is squared dx. That's what it is. That's c squared. That's what we're doing. The reason we're squaring it is because we want to make it into a form that we can work with. At the very end, we're going to undo the square, and I'll show that. What we can realize, what we want to do is this looks similar to polar coordinates. We got squares on the top, and yeah, so what we want to do is when we go from rectangular coordinates to polar coordinates, what we got to do is we got to have an x and a y. We got to realize that this part right here can be written in the terms of y. It's just a dummy variable. We can make x's turn into y's, y's turn into x's. It's just a dummy variable. So if we rewrite this, we can rewrite this as the double integral of negative infinity to infinity over e to the negative x minus mu squared plus y minus mu squared over 2 sigma squared dx dy. What I just did is I just combined the two, and you can add these functions. Yeah, so I added the x minus mu squared plus the x minus mu, the y minus mu squared, because when we're multiplying, exponents, you add them, right? So this is what we have now. And recall, we're going to do a little aside here, and we're going to go back and talk about what happens when we go from rectangular to polar, right? Let's talk about that. So we want to go from rectangular, sorry about that, to polar. What happens when we do that? So we're basically taking two integrals, dx, dy, and then we're changing it to dr, d theta. I say dr. Some people use d rho. I like to use dr. R is the radius, and then rho, or theta, sorry, my bad. Theta is the angle. So, but we got to make sure we have a Jacobian because we're changing coordinates. So we have a Jacobian there. So how do we calculate this Jacobian? We're going from rectangular to polar. So in our problem, what do we have? We have x minus mu and we have y minus mu. Wouldn't it be nice, because we know in rectangular to polar, we know that x squared plus y squared equals r squared. But in this case, we have x minus mu squared and y minus mu squared. Why don't we just, instead of making x, let's make it x minus mu? So recall from rectangular to polar, we have the identities, right? Normally x equals r cosine theta. That's just a well-known fact. Just go through pre-calculus. Y equals r sine theta. And then we know that x plus y equals r, let me see, x squared plus y squared equals r squared. So, but in our case, we're going to transform these for our functions here. So we have x plus mu equals r cosine theta. We're just adding a mu, and we're just changing. Think about it like we're changing, instead of the coordinate system here, we have a coordinate system. Sorry about that. coordinate system, normally we start here. We go, like, let's say we go 3 units on the radius, and then we take an angle. Let's say this is a 60-degree angle, but we're just adding mu. Mu is a constant. Remember, mu is a constant, so we can add a mu, put it up here, and then take it out 3 and roll it up here. Same thing. It's not the same thing, but it's just changing. It's like a coordinate system. We're changing the latitude and the longitude, right? We're changing the latitude and the longitude in there. So let me erase that. So what we're doing here, we got y plus mu equals r sine theta, right? And then we have x, let me see. X, wait, is it minus? Oh, sorry, it's minus. Hold up. My bad. Doesn't change anything, though. X minus mu. All right, so, and then x minus mu squared plus y minus mu squared equals r squared, right? Right. Okay. So now recall, we need to compute this Jacobian now. If you don't recall, the Jacobian is really just, when we go from rectangular to polar, it's just r. But for the sake of this video, I want to derive it. So if we use our identities here, we have these identities on the left. So recall the Jacobian equals the partial of x respect to r, the partial of y respect to r, partial of x, sorry, that's a bad partial respect to theta, and partial of y respect to theta. So if we compute these, so we have a function of x. What is x? X equals r cosine theta. What's the derivative with respect to r? Well, r is just r, so we got cosine theta. What's now we take the derivative of cosine, and then what is that? Negative r sine theta. Derivative of derivative of the function y with respect to r. So that's just sine theta. And then what's the derivative of y with respect to theta? Derivative of y is r sine theta. Respect to theta is r cosine theta. Now we take the determinant. That's what these bars mean. We take the determinant. So what do we have? We have cosine theta times r cosine theta minus sine theta times negative r sine theta. What I just did is I took the major axis and I subtracted it from the minor axis, right? That's what we learned in linear algebra and Calc 3, okay? And so what do we have here? We have r cosine theta squared plus r sine theta squared. Recall, cosine squared plus sine squared, that's an identity. Cosine squared plus sine squared equals 1. So we just take the coefficients out front and we have r, right? So when we're taking what we just did is we took these coordinates and we calculated the area that changes between the rectangular to polar, and that's just r theta. No, it's just r. Okay, so come back here. Recall, now we can tackle this problem. Now we got to change to polar. This looks it would be very easily done if we can change this to polar, right? So what we got to do here is we got to realize what we can tackle the limits later. Let's just talk about the limits later. So we have e to the negative r squared because x minus mu squared plus y minus mu squared equals r. Okay? Divided by 2 sigma squared. That didn't change. Okay? And this is all raised. It's just how it is. Okay, dr d theta. Now, think about it. If we're going from rectangular to polar, and the x-axis, okay, let me draw a picture here. We have basically the whole grid. The whole grid is filled. We're going from negative infinity to infinity on the x, and we're going from negative infinity to infinity on the y. So what should our limits of integration be for our polar coordinates? Well, consider the radius, right? We're talking about the radius. Oh, we're talking about the radius. I was talking about theta real quick. The radius goes from 0, from this point right here, to all over. So it should be infinity. 0 to infinity. Now, what about theta? Well, this angle is measured in pi, radians. So it's 0 to 2 pi. All right, let me erase this stuff right here real quick. Boop, 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 boop. All right. Now we're ready to integrate. Okay? We have it all set up. Oh, actually, I did forget the Jacobian. We forgot to put the r right here. Got a little r there. Okay? Because we're going from rectangular to polar. Now, how do we integrate this? This looks kind of messy. Actually, it does look messy. Let me rewrite it, actually. It's a little messy. I don't like how it's negative r squared over 2 theta. That looks better. R. Okay? How do we integrate this? We have an e raised to the r squared. First of all, what are we integrating? We're integrating r. This looks like an integration by parts because we have an r and this function here. But it's actually a u substitution because we have the parts. If we make this part u, then we have r squared. What's the derivative of r squared over 2 theta? It's just r, negative r. But that'll cancel here. So let's go over u substitution. So we have u equals negative 2 theta. 2 sigma squared. Well, remember, sigma is just a constant, so we can treat it as a constant. R squared. Du equals, well, let's see here. What do we have here? Well, we got the 2 comes out front. So we got the 2, 1 over negative 2, actually. 2 theta squared r. And this equals negative 1 over sigma squared r dr, right? Because the 2 cancels with that 2, and then we get this, right? So we want to solve for wait, let me see. Okay. So dp let me see. dr. We want to solve for dr. My bad. Dr equals negative sigma squared over r. Du. Because we're changing the du. We're just replacing that. So now what we can do here is we can integrate this part first. So we got e to the u r negative sigma squared over r du. Well, what do we have here? These cancel, right? These cancel. So now we can bring this out front. So we got sigma squared 0 to infinity e to the u. obviously anything to e to the u is just off du, sorry, is just e to the u, right? So let's bring this again out front, and then e, what is u? What is u? Because we're not changing the limits here. What is u? That's u. So it's r squared negative 2 sigma squared 0 to infinity, right? I'm just taking what we have here, putting it down here. Okay, so let's plug in infinity. What happens when we plug in infinity into this equation? dr, right? This is dr, so we respect to r. So don't ignore this part. This part doesn't matter, okay? So what do we have? Plug in infinity, what do we have? So this is negative, right? This is negative. So this gets extremely small as we plug in. Think about it as like 1 over e raised to r. If we plug in something r here, it's going to get infinity big. So it's going to approach 0. So this is 0. Minus, plug in 0. Well, if we plug in 0, then this is e to the 0, which is 1. So we got 1. So what's 0 minus 1? That's negative 1. So negative 1 times sigma squared is just sigma squared. Okay. So now that's the answer for the inner part of our integral. So we still got the outer part, the d theta, which is pretty easy. So we got sigma squared d theta, integral from 0, wait, what is it? 0 to 2 pi. 0 to 2 pi. So what we can realize, this is just a constant, you know? This is just a constant. And what we can realize here is that this is not a 6, by the way. Sorry. This looks very similar to a 6, but it's just my handwriting. Sorry about that. It's a theta. So what do we got here? We got sigma squared theta 0 to 2 pi. That's what we got. So let's plug in 2 pi. So we got 2 pi theta, no, sigma squared. Sorry, I keep saying theta. And then, well, if we plug in 0, it's just 0, right? So that's what, but what does this equal? What did we just find? We just integrated this problem. And we just found, what did we find? It's very important for us to realize what we just found. Because, recall, this is a function, c squared. That's what we have up here. We changed it from c to c squared, remember that? So this is equal to c squared. What do we want c to equal? We want c to equal this. We want c equals square root of 2 pi theta. If we can prove that c equals this, then this cancels with this part here, and it equals 1. Okay? So how do we get rid of this square? Well, let's square root both sides. Square root both sides, we get 2 square root of 2 pi sigma equals c. And what did we just prove? We just proved that the normal distribution, the area under it, equals 1. So that's the final answer. So that's how we do it. We go from rectangular to polar. First, we got to take the trick of squaring the c part. And then we do all that, and then we get the rectangular to polar, and then we integrate by use substitution, and then voila, we got it. So, yep, that's how you prove that the area under the normal distribution PDF is 1. Thank you guys, and comment below if you have any questions. I'll try to answer them, but that's how you do it. All right, thank you guys, and see you guys later.